Now we will look more precisely at electronic effects. So once again, the same question: which reacts fastest with NaCN? But now we're looking at chemicals that are both types of aldehydes, but the only difference between these two chemicals is this one has a bunch of fluorines attached to it, and this one has a methyl group. So now let's look specifically on how that will affect the reactivity of the carbonyl group. Once again, we know that Cn- will be attracted to the delta positive carbons here and here. But which one would it be more attracted to? So for this, we have to look at the difference. And this is the fluorine groups that are carbon. So we look on the periodic table. And on the periodic table, we see that fluorine is towards the top right of the periodic table in the 7th group. And we know that fluorine, therefore, is the most electronegative element on the periodic table. That means it attracts electrons to itself stronger than any other atom when it is in a molecular environment. So here it is in a molecule, and it's attached to the carbon, this carbon, and therefore fluorine is going to be really pulling electrons to itself, and there are 3 fluorines indeed. So these 3 fluorines are all going to be delta negative, and this carbon is going to be very seriously delta positive, because it's not just attached to one electronegative atom, it's attached to 3 of the most electronegative atom on the periodic table. So this carbon is going to be very delta positive. The carbon next to it, because this is very delta positive, what will it do to electrons? It will attract electrons to itself, because the more delta positive it is the more that it will attract electrons to itself, because opposites attract. So these electrons are going to be pushed even increasingly towards the CF3 group. Therefore, carbon, which was delta positive before, because we saw that carbonyl groups have delta positive carbons, because it was delta positive before, now it's even going to be more delta positive. It's as if by having this group here, which is drawing electrons to itself, it sort of souped up this carbon and made it even more delta positive than it was otherwise. Therefore, for Cn-, this carbon will be even more attractive than this carbon. Just as in the previous example with the ketone, Cn- will react with the ketone even though they're steric hindrance, but it just won't react as quickly or as frequently as it would with the aldehyde. Well, in this particular situation, this delta positive carbon is extremely attractive for the Cn- nucleophile. So it definitely will come in here frequently, faster, but indeed it also will react with this delta positive carbon. Because it is delta positive, it must also react with that. Not as frequently, not as fast, but it definitely would react with that. There is something different about this reaction compared to the other reaction that we looked at with Cn-, and that is that Cn- definitely will come in here. It definitely will hit this carbon. The electrons will definitely pop up, just as in the previous example. The pi bond breaks and the electrons would pop up here. So this would occur. We have this being 1 and then this being 2, and the electrons pop up there. Normally, as in the previous example, electrons popped up, the electrons couldn't come back down because there was nothing else that would have been a good leaving group. Carbon-carbon bonds in the previous example, it's too strong to break when electrons come down. Carbon-hydrogen bond, it's too stable of a bond just to break like that. However, let's examine this particular bond. This carbon is delta positive, very delta positive, as we said before. This carbon is very delta positive. So what do you think about the stability of this carbon-carbon bond? it must be pretty weak, pretty unstable, because we have a delta positive carbon bonded to a delta positive carbon. That bond must be unstable. There must be some repulsion there. Therefore, when the Cn- comes in, hits the carbon, bounces the electrons up, now the Cn- is bonded to this carbon. The electrons up here on the oxygen have the option of coming back down, hitting this delta positive carbon, and knocking out this CF3 group as a leaving group because of the instability of this carbon-carbon bond. We will now look at the production of acetals and ketals. So here we have a chemical. This is an aldehyde, as we saw before, which means it has a carbonyl group, an R group to one side, and a hydrogen to the other side. This is ethanol. It is symbolized as ETOH. Its actual molecular formula is CH3CH2OH. So this is shorthand for ethanol. And this is an acid, H+. So if this was in solution, if you had to try to derive for yourself what would happen in this reaction, you would start by saying, okay, so we have delta positive carbon here, and we have delta negative oxygen. So that's our typical sort of electronics that we write when we think about a carbonyl group, which is the functional group for this aldehyde. Then we would look at the alcohol, ethanol, and we would say that, well, we have a delta negative oxygen there. Clearly the hydrogen would be delta positive. So that would be the electronics. And so we would suggest, knowing that, that OH minus, the hydroxide group, is on our list of very good nucleophiles, clearly ROH is not as good a nucleophile as OH minus because OH is negatively charged. It has a formal negative charge. So clearly it would be more attracted to something that is positive as compared to ethanol, which has a partial negative charge. It's not as highly charged as the OH minus. So indeed it would be attracted to something that is partially positively charged, but not as quickly as, say, if OH minus was involved in this reaction. Nonetheless, we know that this delta negative charge would be attracted to this delta positive carbon. There would be this opposites attract that would happen in this chemical reaction. And if the delta negative charge came here and hit this carbon, we know that the carbon can only be bonded 4 times. So the weakest bond would break, and that would be the pi electrons, which would go up to the oxygen. So we know that that would occur. However, that does not occur very quickly because the oxygen is not formally negatively charged, but it does occur. How can we make it occur quicker? Well, if you look at the reaction, there is a hydrogen there, an H+. And there is some little rules of thumb that you will look at as we progress through different types of chemical reactions in organic chemistry. One of them is that when you look at a reaction, one of the things you should look for is what is the most highly charged species. The reason is, whatever chemical is most highly charged is most likely to react fastest. For example, in this reaction, we have H+, which has a formal charge. Because it has a clear formal charge, it is most likely that it will be involved first in the reaction, which means whatever there is that is negatively charged or partially negatively charged, the hydrogen H+ would be attracted to that very quickly because it has a formal charge on it. And so when we look at the reaction, we see that there is a delta negative oxygen that's there, and therefore this H+ would have some kind of attraction to that delta negative oxygen. And of all the possible things that can occur, H+ being attracted to a delta negative oxygen would be very high on that list and would occur very quickly. Now, if the H+ would be attracted to this oxygen, And of course, as I mentioned before, we really formally should always follow the flow of electrons. So even though we think of the H plus as being attracted to this, we really should draw the arrow in this direction, showing the movement of electrons. And the movement of electrons would be attracted to the H plus. Now, if the electrons, because it's delta negative, if it is attracted to the H plus, and I'll put a 1 here, meaning that's the first thing that occurs in the reaction. So as the electrons are being attracted to the H plus, the bond, the pi bond, actually breaks as the oxygen formally makes a bond with the hydrogen. Now, if the oxygen makes a bond with the hydrogen, because the hydrogen is so highly charged and therefore is the first thing in the reaction to react, as the oxygen makes the bond with the hydrogen, what would be the charge on the carbon? Well, it would be positive. Not just delta positive, formal positive charge on it. The reason is, as the electrons go up to bond with the hydrogen, then carbon only has 3 bonds. Now, when it had 4 bonds, it was neutral, but partially positive. But now that it releases its electrons, if carbon releases its electrons, therefore the carbon will be positively charged. Now, when the carbon is positively charged, that makes it so much more attractive for the ethanol to come in here, because it was delta negative and this was delta positive, and so the reaction would have occurred anyway. But now that the carbon becomes formally positive, this reaction occurs much faster. In other words, the hydrogen sort of juiced up the chemical to make it more attractive for the ethanol to come in and bond. So then what do we end up with? Well, we have our carbon bonded to the oxygen, which has bonded to the hydrogen. Then we have our other hydrogen on the side, and then we had ethanol that just came in. So ethanol just came in, ETOH. So it just came in and it bonded to carbon. So we have the OH group up here, which was formed when the hydrogen went in. And then we have the rest of our chemical, and then we have ETOH. Now, if oxygen, from this oxygen, comes in and bonds with the carbon, gives up its lone pair of electrons to the delta positive carbon, which became formally positively charged. When oxygen does that, gives up its electrons, then the charge on the oxygen becomes positive. If you have any problem remembering that, just think of the fact that when oxygen has just 1 bond to itself, example OH minus, then the charge on the oxygen is negative, formal negative charge. If oxygen has 2 bonds to itself, example H2O, then the oxygen is neutral. Indeed, it has a partial negative charge, but it has no formal charge because water is neutral. And then when you imagine 3 bonds to oxygen, H3O plus, then the oxygen has a positive charge because it gave up its lone pair of electrons. So here's an example. The ethanol gives up its lone pair of electrons. Oxygen has a positive charge. Does oxygen like to be positively charged? Certainly not. In fact, oxygen is a very electronegative element. On the periodic table, it's towards the right and towards the top of the periodic table. And therefore, it is a chemical, it's an atom that draws electrons to itself. So it wants to have electrons to itself. It does not like being positively charged. So once it gets in this situation, it's going to look around for electrons somewhere to draw to itself so that it could maintain at least its neutrality, preferably delta negative. So here, oxygen wants to draw electrons to itself, and the likely culprit will be the proton. In other words, it draws electrons away from the bond between oxygen and hydrogen, and then it kicks out the proton. It kicks out the H+, and therefore it remains ETO without the hydrogen. And so it kicks out the H+. Now you can imagine, because it kicks out the H+, now it is neutral. We see a couple of important points. Number one, we started off with hydrogen as one of our reactants. H plus is produced in the reaction. Therefore, any chemical that we use in a chemical reaction which is reproduced at the end of the reaction and helps the reaction to occur faster, as is the case here with H plus, that is our definition of a catalyst. So here H plus serves as a catalyst. It not only makes the reaction occur faster by juicing up this carbon, turning it into a formal positive charge, but it is also regenerated during the reaction. So H plus is a catalyst for this reaction. Second important point is this is our hemiacetal. You see, when you start with an aldehyde, you're going to end up producing an acetal. When you start with a ketone, you end up producing a ketal, using the same mechanism of reaction. The ketone, the only difference being that it would have an R group here instead of the H. So now we have our hemiacetal. Now we will continue the reaction and produce an acetal. So here we're going to continue the reaction with the same reactants, ETOH and H, with this chemical. Once again, we do the same thing. What is the most reactive chemical here? The most highly charged, again, would be the H plus. Where would H plus be attracted to? H plus will be attracted to something that's delta negative. For example, some of the H plus will be attracted to this oxygen right here. This oxygen, of course, is delta negative. So H plus being attracted to this oxygen, which is delta negative, because of opposites attract, it would form, well, this is OH, so adding H to OH makes H2O. H2O is water. Clearly, water would be a stable substance. So water is a great leaving group. If you can form water which is attached to a carbon nucleus, water would be happy to leave as a leaving group. So if this hydrogen comes in here, attacks the OH, makes water, it falls off as a leaving group, and then the charge on the carbon, once again, is positive, because carbon would only be bonded once, twice, 3 times. So it wouldn't be bonded 4 times. Water left as a leaving group, this carbon would have a formal positive charge. Because it's juiced up, because it's positively charged, it would be the most reactive thing in the vessel. And so the next event that would occur, once again, the second event being the delta negative ETOH, the oxygen being attracted to the positively charged carbon, it bonds, it kicks out its proton exactly like this one did, and then we end up with an acetal. So we have R, C, H, ETO, and then ETO. This is an acetal. The only difference between this and a ketal is that there would be an R group here, and it would have started that way at the beginning of the reaction. The important thing is to understand the steps during the reaction. The most charged substance acting quickest first, and then because it's juiced up, the ethanol coming in and then reacting. And then it happens a second time where the H plus attacks the OH group, forming water, knocks off, then the ethanol comes in and reacts because of a formal positive charge on the carbon, finally producing the acetal. Now you might be asking, well, wait a second. If the H plus is attracted to something that's delta negative, and it attacked this oxygen, forming water, and fell off, why is it that the H plus did not attack this oxygen, which is also clearly a delta negative oxygen, because it's attached to carbon, and because of the periodic table, oxygen being to the right, carbon being to the left, oxygen clearly is going to be delta negative here. Why is it that the H plus doesn't attack this one? Well, based on electronics, if something makes sense, it probably happens. That's the great thing about organic chemistry, is that there's minimal memorization. Most of it has to make sense. And so yes, it is perfectly logical that the H plus would attach to this delta negative oxygen as well. And if it were to attach to this delta negative oxygen, well, that would just make ethanol. That ethanol, in theory, can fall off as a good leaving group, and then it would make this positively charged, and then the electrons from this oxygen might come back down, and then we end up exactly with our reactant. In other words, the arrows that I drew are actually two-sided arrows. The reaction may proceed to the right, as indicated, and as I've explained, but there's also logic to the possibility that the reaction could also go back to the left. And that even goes for the final chemical. Even with this final chemical, the H+, which is regenerated in the reaction because it's a catalyst, may indeed attack any of these delta negative oxygens, thus returning us to this compound, which could in turn, in theory, go back to the first compound. So these are all double-sided arrows because the electronics suggest that either reaction could occur. So once you understand the mechanism of reaction and just have the comfort that yes, if it's delta negative, if I've got a positive charge, then these things would be attracted to each other, and therefore this is the possible result of the reaction. And just by going through the reaction in that sense, then you would be able to understand this. Now we will look at another example of the production of an acetal or ketal. My question to you regarding this particular reaction is quite simple. The question is as follows: true or false? You may want to put this on pause and consider what your response would be. So let's work this out. First of all, let's look at this chemical. Here we have carbon bonded to oxygen, and the carbon has two R groups off to the side. So this compound is a ketone. It has 6 carbons in it, 1, 2, 3, 4, 5, 6. It's cyclical, so it's going to be called something cyclo-hex. And it's a ketone, so it ends in -one. So this is called cyclohexanone. Here's another chemical, and it has 2 OH groups. When you have an OH group, it's an alcohol. When you have 2 OH groups, it's called a diol. So here we have a ketone plus a diol, and we have a catalyst H+. So what's the first thing that's going to happen in this reaction? Well, clearly the H+ will be attracted to something that is delta negative. So we have a delta negative carbon oxygen here. We have delta negative oxygens here because this oxygen is attached to a carbon. So this is delta negative, and this is delta negative. So here we have our first major lesson in terms of chemical reactions. You see, when this H+ is attracted to a delta negative oxygen, and it has obviously several choices. When you look at an organic chemistry reaction, it is very important to look at the electronics in order to see what would be attracted to what. But sometimes when you have all these choices, you have to look at what would be the stability of the product. In other words, that is going to help you to decide whether or not the reaction can occur, is whether or not the product is stable or not. Because if the product that you produce in your reaction is terribly unstable, then what's the chances that that would actually occur? It would be very, very low. So in this particular instance, if H+ was to attack an oxygen here, well, that would form water. And we said already that water is a great leaving group. So if it were to attack this oxygen, it forms water, it leaves. But if the water was to leave, then the carbon, which is here, would be positively charged. Not just partially positively charged. It would have a formal positive charge because it lost its electrons. It lost the bond that it had with this oxygen. So this would fall off as water. It would be positively charged. That carbon would be called a primary carbon because the carbon here would have only one bond left to itself from an R group. If a carbon has one bond to it from an R group, it's called primary. 2 bonds from 2 R groups to the carbon, that's secondary. 3 bonds from 3 R groups to the carbon, that's tertiary. If the water falls off and this is a positive charge on this carbon, that would be called a primary carbon, also called a primary carbocation, because it would be a positively charged carbon, so it's the primary carbocation. Primary carbocations are very unstable. So that's a line to remember. Tertiary carbocations are much more stable, much more stable. And of course, secondary carbocations are in between primary and tertiary carbocations. Some secondary carbocations being more stable than other secondary carbocations. But the point, the bottom line is, primary carbocations are very unstable, tertiary carbocations much more stable. So producing a primary carbocation would be very unstable, meaning that the hydrogen attacking either of these OH groups is a highly unlikely event because of the instability of the product. We will discuss primary and tertiary carbocations again shortly. Nonetheless, so we have a delta negative oxygen here, the H plus there, the most highly charged thing being the H plus, as opposed to other things in the reaction. Therefore, the delta negative oxygen, the lone pair electrons on this oxygen would be attracted to the H plus. That's breaking this bond, exactly like the previous reaction with the acetal, though now we're looking at a potential ketal being produced. So once the bond is broken because of the H plus, producing OH, the charge on this carbon would therefore be positively charged because the electrons were given up so that this oxygen can bond to OH. So let's look at that. So we have the oxygen here that would bond to the hydrogen. This bond would therefore be broken in order to allow the oxygen to bond to the hydrogen. This carbon therefore becomes positively charged, a formal positive charge on this carbon. And this carbon would be indeed called a secondary carbocation. It would have two R groups, one R group up here, one R group down here. In other words, group of alkanes that are bonded to this carbon, and therefore it's a secondary carbon, much more stable, much more stable than it would have been had a primary carbocation being produced. So we have our secondary carbocation there. What is the most charged thing now in the reaction? It would be right here. So it is going to want electrons, and electrons can be supplied from the diol because these are delta negative oxygens. So one of the oxygens, either one of these oxygens, would be attracted to this carbon like so, and it would bond. It would give up its electrons to the carbon, and therefore as it gives up its electrons to the carbon, the oxygen once again would become positively charged, a formal positive charge. It doesn't like that, so therefore it kicks out the proton, it kicks out the hydrogen. So then as a intermediate to this reaction, we're going to get this bonding here, kicking out its hydrogen. So the intermediate of the reaction would be as follows. We would have, I would draw it up like so. We would have obviously a little bit distorted, but nonetheless we have the OH group here, and then we have the oxygen here, and then the OH of the diol. So you see that the oxygen from the diol comes in, bonds to the carbon, and then we have our OH group here. So this would be the intermediate of the reaction, and in fact this is what we would call a hemiketal, halfway towards producing a ketal, even though this is a cyclical compound. So now, once again, because the acid has been regenerated, the H plus has been regenerated in the reaction, we have H plus floating around in solution. Once again, the H plus would be attracted to anything which is delta negative. We have delta negative here, we have delta negative here, we have delta negative there. So the hydrogen could be attracted to any one of these. Now, if the hydrogen attacked this, it would make water. This would fall off. Primary carbocation. Very unlikely. If the hydrogen were to attack this oxygen, well then it would just produce OH again here. That is our diol. So it would regenerate our diol, and then this can also be kicked out. The oxygen can make another double bond with cyclical group here, and therefore we regenerate our original reactants. So the arrows are double-sided. Indeed, the hydrogen may indeed attack this oxygen and then form the diol and then regenerate our original reactants. However, sometimes the hydrogen would attack this oxygen here, and therefore by attacking this oxygen here, forming water, falling off as a leaving group, and when this falls off as a leaving group, as water falls off, then the charge on the carbon here would be positive. So in other words, you would get this falling off here, we would have a positively charged carbon here, and because we have delta negative here, positive charge here on this carbon, well, of all the reactions in organic chemistry, among the fastest reactions would be an intramolecular reaction. In other words, if you were to have two chemicals that are floating around in solution, one positive, one negative, yes, they are going to be attracted to each other and you'll have a reaction, and it would take a certain amount of time. But imagine if one chemical within itself had positive and negative charges, how fast that reaction would be. That would be extremely quick. So we have a delta negative oxygen right here. We have a positive charged carbon right there. So it's really juiced up. It's ready to react. So this would be an extremely fast reaction in which the lone pair electrons on the oxygen, because it's delta negative, is attracted to the positive charge here. Bang, it reacts. Knocks out the proton, and therefore, if you just use your imagination and twist this chemical a little bit, you end up with this as your final product. And so, classic situation for the MCAT exam, they love to take a reaction which you understand, which you know how the different chemicals come together in terms of acetals or ketals, and then they'll just take a chemical just a little different, a little bigger than you're used to seeing, or different shape or whatever, and therefore see if you can use your imagination, but use the same basic organic chemistry knowledge with the basic rules that we looked at. Most charged item or species reacts fastest, positive to negative, and primary and tertiary carbocations, etc. Just knowing the basic rules will allow you to do an innumerable number of reactions. Now let us continue and look at some tertiary and primary carbocations and their reactions in terms of nucleophilic substitution. We will now look at a whole classification of reactions called substitution reactions. Now these substitution reactions are divided into SN1 and SN2. And SN1 reactions stands for substitution nucleophilic first order. So these are nucleophilic substitution reactions, first order. First order means that the reaction depends on the concentration of one compound. So we're going to look and see why these are called nucleophilic substitution reactions and why they are first order reactions. First off, here we have a tertiary compound. And from before, you can know that the R group stand for alkyl groups and the X group stands for a halide. So we know that halides like chloride, bromide, and fluoride, these are chemicals that are very electronegative and draw electrons to themselves, and so they would be very happy to have this sort of reaction in which this dissociates. And so what we would get if this were to dissociate is we would get R, C, R, R, and this carbon, if this were to dissociate, would now be positively charged because it would give up its electrons to the more electronegative element, and then we would have plus X minus. So from what we discussed before, I said that tertiary compounds are much more stable than primary compounds. In fact, you can consider tertiary compounds as seriously relatively stable compounds. And so this would be called a tertiary carbocation. And this tertiary carbocation is quite stable. The reason is the following, and here is a statement to memorize, and that is that alkyl groups are somewhat electron donating. And it's just like that that you should remember that statement. It's not that alkyl groups are very electron donating, because they're not. Alkyl groups are somewhat electron donating. And here is an example where that feature of alkyl groups is very important. We have 3 alkyl groups surrounding a carbon which is positively charged. Normally carbon would not want to be positively charged. It doesn't mind being partially positively charged, but to carry a positive charge on itself alone, it doesn't like that. However, if it's surrounded by 3 groups, and each one of these groups are contributing electrons to the carbon, it's like carbon has a fire, and each one of these groups are helping to quell the fire, to lower the heat, so that carbon can be as comfortable as possible in the situation where it's holding on to a positive charge. And so when carbon is surrounded by 3 alkyl groups in a tertiary carbocation, it is relatively stable. So this is an important point about the reaction, is that this dissociation will occur spontaneously because the tertiary carbocation is relatively stable. Now let's say, for example, there is an OH minus group in solution, which means they say there's sodium hydroxide or potassium hydroxide. In the MCAT, they're not going to necessarily put a juicy lone pair of electrons on an OH minus and say, go for it. They're going to say something like sodium hydroxide is in solution, but for you, sodium hydroxide should mean Na plus and OH minus. And Na plus is going to sit off to the side and do nothing because it's a spectator ion. And OH minus would be actively involved in the reaction because we know it is a good nucleophile. So when we see this situation, a good nucleophile, a positive charge, clearly this negative charge would be happy to go in here and attack the carbon. And so what we would end up with is our carbon, R, and then OH. So this would be called, because it's an OH group attached to the carbon, it's an alcohol. Because there's 3 R groups, it's a tertiary alcohol. So this would be called a tertiary alcohol. Now, this is called nucleophilic substitution because at the beginning of the reaction, we had an X group attached to the carbon. At the end of the reaction, we have an OH group attached to the carbon. So there's been a substitution at the carbon nucleus from X, a halide, to OH, the nucleophile. So that's the first thing, nucleophilic substitution. The second issue is that of first order. The reason why it's called a first order reaction. And that is because this step here is a very slow step. This step here, OH minus, formal positive charge, attacking a formal positive charge, that happens very quickly. So this happens very quickly, but this goes very slowly. This is called the rate determining step. It is the slowest step in a series of steps for a particular reaction. That is called the rate determining step. In fact, every time I think of a rate determining step, I think of a wonderful program on television, family show, The Simpsons. Actually, I don't really believe that, but nonetheless, The Simpsons, there was this episode in which Bart was the only person in town that had the same blood type as Homer's boss. And Homer, trying to get in good with his boss, wanted to get a sample of blood from Bart because the boss was dying from some blood disease, which is in the made-up world of cartoon. Nonetheless, so Homer wanted to take some blood from Bart. So they went into an ambulance and they withdrew blood from Bart. And of course, he faints because he didn't have enough blood left in him. But nonetheless, they withdrew the blood very quickly. They packaged it very quickly, just took a few seconds. They passed it off to another ambulance very quickly. The ambulance went off to the hospital, just took a few seconds. Then once it got to the hospital, there was a porter waiting, took the blood, ran to the elevator, just took a few seconds, got to the elevator. Somebody was waiting in the elevator, took the blood, and started looking around the elevator, singing a song, whistling, and having forgot to press the button on the elevator in order to go to the proper floor. And so let us imagine the following. Let us imagine that every single step after taking the blood from Bart took a few seconds. And then the person in the elevator hung out there for half an hour. Then, when you were to discuss what was the rate of the reaction, how much time did it take to get the blood there, say the time took, whatever, 32 minutes or 33 minutes or whatever, but it took a half an hour for that person in the elevator. Well, what did the rate of the reaction depend on? It depended on the slowest step, because the rate of the reaction mostly depended on that slowest step. And this is the case here. This is the guy in the elevator who's hanging out. Because even though a tertiary compound is stable, it's not a very quick reaction for this thing to just dissolve on its own. It's not fast. But OH minus, a nucleophile, a great nucleophile, going in and attacking something that has a formal positive charge, not just partially positive, that is extremely fast. So clearly this is the slowest step. This is the rate determining step in this reaction. Because it's the rate determining step, because the rate of the reaction depends on this compound, on what happens with this compound, this is a first order reaction, SN1. Nucleophilic substitution, first order. Depends on this, not on the OH minus. Furthermore, just as an interest's sake, you will see later that this chemical is too hindered, too bulky for an SN2 reaction to occur. Nonetheless, let's move on to an SN2 reaction and see how they occur. Now we will look at an SN2 reaction. So this is nucleophilic substitution second order. Now the rate of the reaction would depend on two compounds. That's why it is a second order reaction. So first of all, if you look at the reaction that we're going to see, this is the identical reaction that we just did, except that instead of it being a tertiary carbon with 3 R groups, we see that 2 of the R groups have been replaced by 2 hydrogens, so that this carbon is considered to be a primary carbon. Because it's a primary carbon, when this is placed in solution, this X group does not just ionize. It doesn't just dissociate. And because it does not dissociate, because it would be a primary carbocation. And a primary carbocation, as we said earlier, is just too unstable. And the reason it won't happen is because the R group, being a little bit electron donating, somewhat electron, is just not enough to quell the fire of the positive charge. You need more R groups than just having one. So in reaction, we have this compound and the OH minus group, just like we had previously. And what would happen here is that, well, this carbon would be delta positive. This X group is delta negative, since it is a halide to the right of carbon in the periodic table. And so these electrons would be the first thing that would be attracted. So that's the first part of the reaction. I'll put a 1 here as being the first part of the reaction, as it is attracted to the carbon. And then carbon can only be bonded to 4 different things. The weakest bond must break. The bonds between carbon and hydrogen, carbon and carbon, are generally pretty much equally shared. But the bond between carbon and a halide is unequally shared. And not to mention, halides are on our list of good leaving groups. So when the OH minus comes in, hits the carbon, one of the bonds must break. It will be this one. It breaks. So that would be what happens. And the X group, the leaving group, leaves. And so then we would have the OH group coming in and bonding to the carbon. 2 things to show you about this. One thing is that I would like to show this to you in slow motion as the OH group is coming in and hitting the carbon. So let's look at what we would call the transition state. So here are hydrogens. Here's another hydrogen. Here's an R group. So this is this part of the molecule, CH2R. And then here's the X group here. The OH minus group comes in from behind to knock up this out. See, the the carbon is bonded here to the X group. In order for it to be dislodged, the OH minus group has to come in from behind and hit the carbon and knock out the X group. So as the OH group comes in and starts bonding to the carbon, the bond between the X group is being broken. So this compound here, as it's being written, which would be negatively charged because the OH minus group is coming in with its electrons, this compound is called a transition state, meaning this is what we're going to see before the final product, because this is what's happening as the OH group is just bonding, coming in, bonding, it's breaking off the X group. So it's as if we're watching what happens here in slow motion. This sort of occurs simultaneously, even though I've written 1 and 2 in terms of the sequence of events. The bond starts to break more or less simultaneously, and then the X group is popped out. And so the final reaction, what we have is RCH2. We will have an OH group here plus X minus. So here we have a primary alcohol as our product, and we have the X minus, which was kicked out. Now notice, we started with an X group at the carbon nucleus. We end up with an OH group, nucleophilic substitution. And the reaction depended on these two compounds. We have to have one coming in and one leaving. So it required these two chemicals in order for this reaction to occur, because this didn't just fall off. There was no rate determining step in which something just came apart and then something came in. No. This reaction required both of these compounds, SN2, nucleophilic substitution, second order. The rate of the reaction depends on the concentration of both of these compounds, producing our primary alcohol. Next, we will look at the orientation of these chemicals. I'm now going to comment on the orientation of these chemicals. You see, this is the tertiary compound that we initially looked at for the SN1 reaction. And then it ionized, produced a tertiary carbocation, and then it was attacked by OH minus. However, when it ionized, it produced that tertiary carbocation. But what we didn't really look at is the fact that this is a three-dimensional compound. It's not just flat on a board. It really is a three-dimensional compound. And so if you can try to imagine it in 3 dimensions, because carbon is at the center of a tetrahedron, you would be able to imagine that, and a tetrahedron sort of being a pyramidal shaped structure with a triangle at the base, and then there's a top with the carbon in the middle. And so you have to imagine that when the OH minus attacks the carbon, and this is the positively charged carbon here, the OH minus, which will be making its attack, it can attack either here or on the other side. There is no reason why it should attack one side any more or less than the other. In other words, the orientation of the molecule in the end may have the OH group attached to the right side, which is what I showed on the board when we did it just moments ago, or it might be that the chemical actually has the OH minus attached to the left side, which is 50% probability. If all these R groups are the same, which they are according to the way I've written it, then there's a 50% probability that the OH group will attack on this side or attack on that side. In other words, it doesn't have to attack on the same side where the X group was lost, because the chemical is 3 dimensions, so it can come in on the other side. Well, if the OH group attacks on the right side, then we say that yes, it was nucleophilic substitution, and the chemical was not inverted. It was not inverted because it has the same orientation as the original chemical, with the OH group attached on the right side. If the OH group attached to the left side, then we say it's inverted, because the X group was on the right side at the beginning. So if you end the reaction and you have the substituent attached to the left side, which would be the case if it came in here, then we say that the molecule was inverted. So the molecule can be inverted or not inverted, and there's a 50% chance of each. If you have a mixture of compounds where half of them are inverted and half of them are not inverted, which would be the case in this reaction, we call that a racemic mixture. It's a racemic mixture. It's also called a racemate. So that would be called a racemic mixture or a racemate. Now for SN2 reactions in which the OH group, the OH minus group, enters by backside displacement according to the molecule that we looked at in slow motion, where the OH group has to come in from behind to hit the carbon and knock out the X group. Because it always comes from backside displacement in an SN2 reaction, whatever side the X group was on, the OH group, the new substituent, will be on the opposite side. Now, of course, when we did the reaction just moments ago, I kept the same orientation of the molecule only because that's the way we do it in shorthand. We don't usually write molecules with the substituent on the left, but that's not important for you to memorize. But the point is this, that in reality, when the substituent or the nucleophile comes in an SN2 reaction, there's always going to be an inversion of the molecule. So that means the actual final molecule will look like this with CH2R. So that the actual molecule will have the OH group on the opposite side of the chemical. And so that's important because that means that SN2 reactions produce molecules which are always inverted because of the backside displacement, whereas SN1 reactions can have molecules that are inverted and not inverted. And if there's an equal amount of each, then we call that a racemic mixture. Now we will look at carboxylic acids. So here's the functional group for carboxylic acids. It's a carbonyl group with an OH group. Carboxylic acids are the most acidic organic chemical. Now, we have to keep this in perspective. Yes, it is the most acidic organic chemical, but compared to inorganic chemicals, the organic acids basically are not very acidic. They're weak acids, but they're very important in organic chemistry. So when we talk about organic chemistry, these are the most acidic organic chemicals. Why are they so acidic? This in itself is a very common MCAT question. Why are carboxylic acids so acidic? And the reason is because of its gain in resonance energy. So remember, an acid, one of the definitions of an acid is that it is a proton donor. So we have to imagine if this carboxylic acid were to give up a proton, release a proton, what would be the result? What is the stability of the product? One of the points we made earlier. So the stability of the product, this is what we would get. We would get this. O minus, which is, of course, equivalent to writing this. And this is what's called resonance structures. Here are two equal structures we can write at the moment that the proton is delivered, and we're looking at the stability of the product. We get this anion. You may remember from high school, an anion, R negative, AN, ion, R negative ion. So we have this anion being produced. And this anion, because it's called a carboxylic acid, this anion is called the carboxylate anion. You'll hear the word ate at the end of many types of anions. So this is called a carboxylate anion. So you see that there are two equal ways of writing this carboxylate anion. There's no reason why there should be a double bond up here and not down here, or vice versa. And as we saw in general chemistry, it is not the case that when you write resonance structures, two equal structures for a compound, it is not the case that it is resonating back and forth between these compounds. And in truth, there is no double bond here, there is no single bond, but rather, in truth, if we were to really write this the proper way, we would see that there is sort of delocalization of the electrons in the bond between the oxygens, so that there is no single bond or double bond in the carboxylate anion, but truly there's about a bond and a half for both of them at all times, because the electrons are delocalized. It is this, we call this a gain in resonance energy. Once it releases the protons, and you can have these two equal resonance structures that we can write for this carboxylate anion, we say there's a gain in resonance energy. It is more stable, therefore it is more apt to lose the proton. And therefore, that is why carboxylic acids are 10 to the 10 times more acidic than its native alcohol. Meaning, if there's an alcohol with the same number of carbons in it, compared to a carboxylic acid, the acid is 10 to the 10 times more acidic, which is really an incredible number. And the reason for that difference is because of the gain in resonance energy when the carboxylic acid loses a proton. The next thing we'll look at is what can influence the acidity of a carboxylic acid. My question to you is straightforward. Which of these two compounds is more acidic? You may want to pause and consider your response. Well, first of all, if you look at this particular compound with two carbons, and it is a carboxylic acid because of this functional group, this is a famous carboxylic acid called acetic acid, found in, of course, vinegar. This here is different, and the only difference is that we have an X group here. There is a halide, therefore, which is present here. So therefore, all we need to do is to look at what the presence of this halide would do to change things in this chemical. Then we would know which of these two would be more acidic. Well, we know that a halide is delta negative, and we know that it is drawing electrons to itself. So it's pulling electrons to itself. So this compound, compared to this compound, would be a compound that would love to have electrons in the compound. Well, how could it get more electrons in the compound if it kicked out a proton? In other words, if it were to release this proton and have the formal negative charge like the carboxylate anion, which we just looked at, then that would be able to satisfy one of the desires of an electronegative atom. By adding an electronegative atom, it is going to increase the acidity of this compound because it is more desirable for it to release a proton. Furthermore, consider the following. What is the charge on this carbon? It would be delta positive because it's attached to a delta negative element. Then the charge on this carbon here is also delta positive because it's attached to delta negative elements. Well, we have two delta positive carbons which are attached to each other. What do you think about the stability of the neutral molecule? Very unstable. There are two delta positive things that are attached to each other, and we know that opposites attract, like charges repel. So this neutral molecule is very unstable. But if it were to kick out the proton and get a negative charge, well, we know that we have this CH2 here, we have the carbon here. We know that this would create a situation where we have an O minus, and we know that this creates a resonance structure in which the electrons are delocalized, meaning this delta positive carbon, its positivity will be reduced by the proximity of the electrons which are moving up and down the system, reducing the positive charge, reducing the repulsion between these two carbons. Therefore, this compound is more acidic, definitely, than acetic acid for two reasons. One is that the neutral form of the compound is unstable, and because the anion has increased stability.